Welcome to Lecture 8 of Unit 1 of 16204 Differential Equations 1. And so in the previous 7 lectures we have talked about methods that we can use to solve first order differential equations. And so we've used techniques such as separation of variables, integrating factor for linear ODEs. If we have an exact equation, we looked at a method to solve exact equations and a few substitutions. And then finally we did define a method to solve linear and nonlinear ODEs using integrating factor methods depending on the exact type of ODE you were looking at. So we have multiple options to find the exact or analytical solution to differential equations if we can first classify that differential equation. However, not every differential equation actually admits an analytical or an exact solution. Okay, so sometimes we need to use geometric approaches, or in other words, graphical approaches to not solve a differential equation, but at least understand what's going on and understand how the system or the equation is behaving. Okay, so today we're going to look at two specific cases. We're going to look at a geometric approach of understanding differential equations using something called direction fields and defining things such as solution curves. And then we're also going to look at something called an autonomous first order differential equations, which are a special case of first order ODEs. Okay, so as I said, for some differential equations it is impossible to find an algebraic solution or an exact solution, but we can still learn about the dynamics of the equation using a graphical method. So let's just, this is really a method is going to be applicable to first order ordinary differential equations. So equations of this form: dy by dx equals some function of x and y. So given any first order ODE, we can sketch something called the direction field for the equation. Okay, and to do this we have to think about what this term dy by dx is actually telling us. Okay, this is actually telling us, okay, well, given that we have a small change in x, or given that we change the value of x a small amount, how much does y change? Or in other words, sometimes at high school you can think of it as, what is the slope? You can think of dy by dx as what is the slope of the function at some point in space. Okay, so what is the equation dy by dx specifies a slope at each point in the xy plane. And so of course this only works where the function is defined, so we can't have a function that's going off to infinity. Or for example, we can't have a function such as the logarithm. We couldn't use negative values in the logarithm. So this direction field approach applies wherever the function f of xy is defined. So this function f of xy, the right hand side of the equation, is going to tell us what the value of the slope is at every point in the plane where the function is defined. Okay, and we can plot short line segments at multiple points on a grid where the slope of each line segment is given by the slope calculated from the ODE. Or in other words, the value of this function f of xy at these points x and y, where you can plot multiple points on some grid. Okay, and such a plot is called a direction field. Okay, so I'm just going to give you an example here. So let's look at this equation dy by dx equals 0.2 x times y. So this is actually a separable equation, so we can actually solve this equation exactly if we wanted to. But just as an example, we're going to look at the direction field of this ODE, first order ODE. Okay, so the function f of xy is just the right hand side of this differential equation. Okay, this ODE is written in normal form. So the function f of xy is just the right hand side of the equation. You'll also note that this function f of xy is defined for all finite values of x and y. There's no points here where the function is undefined or is going off to infinity. Okay, so we can make some observations about this ODE. So on the x and y axis, so the x-axis is where y is equal to 0, and the y-axis is where x is equal to 0. But in other words, on the x and y axis, x is 0, y is 0, this function is going to be 0, okay? Because we're multiplying 0.2 times either 0 or 0. So along the x and y axis, this function is 0. Of course, that means that any line segments, well, a slope of 0 is just a flat line, right? If a line has a slope 0, it's just a horizontal line. Okay, so I can plot these on a graph to represent this this horizontal or this the solution of this ODE is flat at that point or horizontal at that point. Okay, so I haven't just plotted line segments here, I've plotted arrows as well. I've put arrow heads on the end of the line segments because it's actually going to be a little bit easier to visualize later on if I do this. Okay, but along the x-axis here, and along the y-axis, the function is equal to 0, so the slope that we're drawing is going to be horizontal. Okay, now if we look in the first quadrant, so the first quadrant, well, in mathematics usually we start from the positive x-axis here and move anti-clockwise. So the first quadrant is this top right corner here on the graph. And in this first quadrant, x is greater than 0, so x is greater than 0, and y is greater than 0. So we know that this function, f of xy, is going to be positive, right? So 0.2 times something that is greater than 0 times something that is also greater than 0, f is always going to be greater than 0. So the function f is always positive. Okay, and the second, well, I can... So what does that tell us? Well, it tells us that the slope of our line segments are always going to be positive, pointing upwards like this. Okay, there's never going to point on some angle that is pointing downwards. Okay, so we have to walk. If we were walking left to right, we have to walk up the hill, up the slope. We never get to go downhill in this first quadrant. And we can also notice that when the value of x is fixed, so if we just choose a value of x here, and if we increase the value of y, the slope gets more steep, right? Because if I fix the value of x and I increase y, then this function f is getting the numerical value when I put in those two values of x and y is going to be getting larger as y gets larger. So you can see here that these line segments are getting steeper for fixed x as I increase y. Okay, and similarly, the same thing happens if I fix the value y. So if I just look at this line here, y equals, I don't know, y equals 1 over here. If I fix y and increase x, then the same thing's going to happen. My function is going to increase as x increases. So we're going to get if we're walking left to right, these line segments are going to get steeper and steeper. Okay. And so then, of course, as you increase both x and y, then the line segments become more and more vertical or more steep, still with a positive slope in this quadrant. Okay, so we get something that looks like this. Okay, so it almost looks like our equation. If we were walking along this path here, we would start horizontally on the y-axis. And then we'd move further to the right and move up here like this. We'd follow this sort of path. Okay, we can repeat this analysis for quadrants 2, 3, and 4. So repeat for all the quadrants, and you can develop a direction field for this ODE that looks something like this. Okay, so we've got these line segments now for multiple values of x and y, and yeah, you can see the general behavior. If you started up at the top left here in the second quadrant, then well, you would just sort of follow this circular path around here. Okay, so even though we haven't actually solved this differential equation, just looking at the visual representation of the slope of this using this direction field method, it gives us an idea for how the ODE behaves, right? So if I start at this green point on the graph here, and I follow that direction field. So for example, if this was the direction field of an ocean, for example, and I put a marker buoy or a marker tracer fluid or something, or even anything that's just floating around following the ocean, then we'd expect that this thing would just follow the direction field. This tracer would follow the direction field. So it would move something like this. Of course, we can actually find the exact solution to this ODE here because it is separable. And so the exact solution, let's find that. It's a separable equation. We can divide through by y on the right hand side, and we get dy over y. Multiply through by dx, we get 0.2x dx. And so the solution, the one parameter family of solutions to that ODE, is some integration constant times the exponential of 0.1 x squared. Okay, so the solution to the ODE is given here. If we now add in an initial condition to form an initial value problem, then we can find the value of that integration constant C naught, right? So for example, if we had the initial condition when x equals 0, y is equal to 0.3, then we would find simply that C naught, the constant, is equal to 0.3. So therefore our first solution, which is why I've labeled it y1 to be our first solution, is equal to 0.3 times the exponential of 0.1 x squared. Or for example, if we had a different initial condition, let's say x equals 0, when x equals 0, y equals negative 0.3, then we'd also find that our integration constant, or our constant in that solution to that ODE, is negative 0.3. So we could form a second solution to the second initial value problem, which is negative 0.3 e to the 0.1 x squared. Okay, and so I can plot these two solutions to the two initial value problems on top of our direction field. Okay, and if I do that, you can see that the solution curves, so these things in black here are called the solution curves because they are the graphical representation of the exact solution of the ODE. So these black lines called the solution curves, again, they follow the direction field. Okay. So if we have an ODE, we can get what we call the general solution to the ODE. So that's just the solution with a parameter, with the one parameter family of solutions. But the solution curves themselves are the particular solutions to the initial value problem. So once we've given our ODE an initial condition, so first order ODE, so one initial condition. So once we've given our first order ODE an initial condition, then these solution curves are simply the particular solutions. For example, y1 in the first initial value problem and y2 in the second initial value problem. Okay, so the direction fields are quite useful because they essentially show us the shape of the solution curves. Okay, so in this case we could actually solve this differential equation. So, well, the direction field is a nice graphical way to look at the solution, but often we can't find an exact solution to our differential equation. So the direction field can be really useful for understanding what our solution curves are going to look like. Okay, so there are a couple of other interesting things that we can do using this graphical method. So we can define these things called isoclines and stationary points. So an isocline is a curve or a line where the function, the right-hand side of this equation, f of xy, is equal to some constant c. So any constant. C is just some real number for all points on the line. Okay, so for example, with our ODE, dy by dx equals 0.2 x times y, if our function, which is the right-hand side of that ODE, if that is equal to some constant, then I can rearrange that equation to find an equation for the line, okay, this isocline. Okay, so if I do that, if I simply divide c by 0.2x, then I get y is equal to this constant c divided by 0.2x. Okay, so the isoclines of this differential equation are governed by this equation here. Of course, you have to be careful that this equation is defined. So this is obviously not defined for x equals 0 because we get we're dividing through by 0 there, so there's a problem there. Okay, so this equation represents a one-parameter family of isoclines. Okay, so if we whatever value of c we choose, then we're going to get a different isocline. So if I plot those on our direction field here, okay, so in pinky purpley color we've got the direction field. The black lines are representing the solution curve, so the exact solution of the differential equation. And the green dotted lines, that is the isoclines for, and so I think there's 4 or 5 on there. That's for different values of that constant c. Okay, so the point is an isocline. Every point along this line, so let's just look at this isocline in the top left here, in the second quadrant, every point along this green line, along this isocline, has the exact same slope, and that slope value is equal to c. Okay. So, so let's, just to be clear, each of these individual isoclines have different slopes, or a different value of c, but on the same isocline, every point on the isocline has the same slope. Okay, so well, let's just make this up. So let's just say every point on this green isocline in the top left in the second quadrant has slope, let's just say negative half, just to make up a number. Every point on this green isocline in the first quadrant in the top right here, let's say that has positive 0.5 slope. Okay, but the point is, I think the point is clear. Every point on the isocline has the same slope. Okay, so again, this graphical method can be really useful to study the behavior of a differential equation, especially in the case that we can't solve this differential equation. So all my graphs here have been plotted using MATLAB, and you'll be using MATLAB for various parts of this course. So at the end of Unit 1, I'll do some MATLAB tutorial for the topics we've covered in Unit 1. So that'll be in a following video, probably in week 3. Okay, so now we should be able to draw some direction fields and their associated curves. But let's even simplify things a little bit more. So in the previous direction field method works for functions of 2 variable x and y. What if we have a differential equation that only depends on one variable, and that is the dependent variable? So such an equation we call an autonomous differential equation. Okay, so if the right-hand side of a differential equation is only a function of the dependent variable, then the differential equation is autonomous. We call it an ADE. So if we focus on first order autonomous differential equations of this form, so dy by dx, so first order, equals some function of y, so there is no x dependence here at all, so yeah, only a function of y, then we're just going to focus on these autonomous first order differential equations. So for example, if I give you the differential equation dy by dx equals 1 plus y squared, and the differential equation dy by dx equals 0.2xy, the first is autonomous because this right hand side is only a function of y. Okay, but the second is non-autonomous because, well, we have a y here, but we also have some function of x. Okay, so in fact, this differential equation is the one that we plotted the solution curves and the direction field for before. So that differential equation was non-autonomous. So the special thing about the autonomous differential equations is that the value of the slope does not depend on the value of x. It only depends on the value of y. Okay. So let's define this thing called a critical point. So a real number c, is called a critical point of the autonomous differential equation. If when you substitute c in terms of for y in the function, the right hand side of the differential equation, we get 0. Okay, and since the right hand side of the differential equation, when that is equal to 0, dy by dx is equal to 0. Okay, so when this right hand side of the ODE is equal to 0, then the slope is equal to 0. So we've got a critical point here. This is what we call a critical point. So if we have this value of y such that the slope is equal to 0, then we call that value a constant solution to the autonomous differential equation. Okay, so if we have y is equal to some number c such that dy by dx is equal to 0, then we have a constant solution. Then y equals c is a constant solution to the ADE, and we call that solution an equilibrium solution. So, for example, dy by dx equals y squared minus 3y. We can pull out a common factor of y there, so that we can write that as dy by dx equals y times y minus 3. Okay, so clearly this is going to be equal to 0 when y is equal to 0, or when y is equal to 3. So the critical points, y equals 0 and y equals 3, these are also equilibrium solutions. So y equals 0 is an equilibrium solution to this ADE. Y equals 3 is an equilibrium solution to this autonomous differential equation, this ADE. Okay, so now that we've defined these things called critical points, we can plot the phase portrait of this autonomous differential equation. So the direction fields that we plotted earlier in this lecture, they were plotted on a two-dimensional plane because we had two variables, x and y. An autonomous differential equation, well, we only have one variable here. We only have y is the only thing that's changed, that affects the slope, the dy by dx. So actually we can plot a phase portrait of these ADEs on a single line. Okay, so let's consider what's happening on either side of each critical point. So this equation we just looked at, this ADE we just looked at, dy by dx equals y times y minus 3, has these two critical points. Let's have a look what's happening to the derivative on either side of these critical points. Okay, so y equals 3, either side of 3 is 4 and 1, just picking any numbers either side of that. Y equals 0, picking any two numbers either side of 0, 1 and negative 1. Okay, well, here is the y-axis, so as we change y, here are our two critical points, 0 and 3. Let's have a look what happens when we substitute y equals 4 into the differential equation. Okay, well, if we do that, y equals 4 minus 3 is 1. 1 times 4 is 4. So our slope, dy by dx, is increasing for y equals 4. Okay? So for y greater than 3, greater than that critical point 3, our slope is positive. Our slope is positive, so the value of y is increasing. So we can put an arrow over here on our phase portrait and say y is increasing as we are whenever it's larger than this critical point 3. Okay, we could do the same for the point 1. So when y equals 1, we have 1 minus 3 is negative 2 times 1 is still negative 2. So dy by dx when y equals 1 is negative, so or it's less than 0, so y is decreasing. Okay, so the value of y, if the value of y is greater than 3, then dy by dx is increasing. If the value of y is less than 3 but above 0, then the value of y is decreasing. Okay, and then similarly we can do the same thing for y equals negative 1. So negative 1 minus 3 is negative 4, multiplied by negative 1 is positive 4. So dy by dx is positive and y is going to be increasing. Okay, so you can sort of imagine what's going to happen here. If you have a y value that is somewhere in the middle of 3 and 0, then you're going to move, the function is going to move towards that critical point 0. Okay, or if you start at, let's say, a negative value of y, then you're going to eventually increase towards that value of 0. So we can plot the behavior of this solution on a graph. Okay, so here's my two critical points, y equals 3 and y equals 0. And so we know that if we start, for example, somewhere near this line, this critical point y equals 3, we're going to move away from that line, okay, and move towards the critical line 0 in some curve. We don't understand how it's going to move or exactly the slope, but all we know is it's going to move away from this line y equals 3 towards that line y equals 0. Or similarly, if we started just above this line y equals 3, then we're going to move away from that line because, well, we showed that for values of y greater than 3, dy by dx is increasing. And then similarly, if we start somewhere down the bottom here, below for negative y, then for negative y, dy by dx is increasing, so we're going to move towards this line y equals 0. And so I can sort of sketch some curves that do that on this graph. Okay. So notice too that for ADEs, they always are separable, right? Because, well, the right-hand side never depends on x, but the right-hand side is only a function of y. So we can always separate these variables, but you may not always be able to evaluate the integral. So drawing a phase portrait like this can be useful to understand the dynamics of the system. Okay, so what's interesting is that if we take this point y equals 0, this critical point y equals 0, if we start on either side of this point, then what our analysis has told us so far, that we always move towards this point y equals 0. So if we start somewhere up here, let's say at y equals 1, then eventually we're going to move down towards that line y equals 0. And similarly, if we start with a negative y, we're going to move towards that line y equals 0. Okay, but the opposite is true for the other critical point y equals 3. Okay, so if we start just below y equals 3, like 2.9999, then we're actually going to move away from that line y equals 3. Okay, we're going to move down towards the line y equals 0. But if we start slightly above the line y equals 3, 3.001, then we're going to move away as y increases. Okay. So there's something interesting that's going on, something that's different between this line, or this critical point y equals 0 and y equals 3. Okay. So this leads us into something called attractors and repellers. So if y is a non-constant solution to the ADE, so this is not a critical point, y of x is not a critical point, but if C is a critical point, then three types of behavior can be observed near the critical point. The critical point can be either asymptotically stable, which we label as an attractor. It can be unstable, which we label a repeller, or it can be semi-stable. Okay, and so let's look at these three potential solutions. So let's suppose that we have an ADE, an autonomous differential equation with three critical points. Okay, so we've got three critical points, y1, y2, and y3. Constant solutions at those points. If we do the same analysis, if we do this phase portrait analysis for the system, and suppose we find that for y1, both arrows are pointing towards y1. Okay, so both arrows are pointing towards y1. So therefore, we call y1 an asymptotically stable attractor. Because the reason I call it that is because if I move away from y1, if I start above y1, then it sucks me back into y1. If I start slightly below y1, then it sucks me back into y1. So every point that is nearby that critical point is moving towards y1. It's being attracted to that point y1. So if both arrows point towards a critical point, we call that critical point an asymptotically stable attractor. Okay, well, what if one arrow points towards a critical point, in this case y2, and one arrow points away from y2? So in this case, if I'm slightly above y2, then I move away from y2, but if I'm slightly below y2, then I move towards that critical point y2. Okay, so it's a mixture of being an attractor and a repeller, and so therefore we call y2 semi-stable. So if one arrow points towards the critical point and one arrow points away from the critical point, then we say that critical point is semi-stable. And so it's probably doesn't take much imagination to understand what a repeller is. So a repeller is when both arrows point away from the critical point. So for example, y3 here, if we're slightly above the value of y equals y3, then we move away from y3. If we're slightly below the value of y equals y3, then we move away from y3. So both arrows point away. We call this an unstable repeller. Okay, so that's all the topics that we had to cover today. I hope that was clear. And again, if you have any questions, please feel free to get in touch or post on the stream site, the forum on the stream site. We have one more class in Unit 1 tomorrow, and then I'll do perhaps some MATLAB examples or Octave, and then we'll move on to Unit 2. So this is good. I think next time we'll also look at some applications of first order ODEs. Okay, thank you very much, and I'll see you in Lecture 9 next week.